Hey there, everyone. I'm going to do a sample question here. I was asked a question by a student that's in the school with me, and I forgot to sort of turn it into a screen recording. So I'm going to do even more than the help I gave there. So I'm going to take this question from lesson 27, and it's in 29 again, because 27 was about scale diagrams, and then 29 is about using components and calculating mathematically what the answer should be. So I'm going to do this question 4 different ways, actually. So first of all, I'm going to do it the way it's written, which will describe whether or not it is addition or subtraction. And before I go on here, I'm just going to we're good. I just want to make sure I copied that file, so I have a blank version of it. All right, sorry. Game on here. All right, sorry about that. I did need to copy that file, and I just modified it a little bit as well. So here we go. This is the question from lesson 27, and it has an airplane flying with a heading of north 50 degrees west from Toronto to Sault Ste. Marie, and then a distance of 500 kilometers. Sorry, it's a distance of 5 kilometers, sorry. And then after that, it flies to Ottawa, which is 750 kilometers east, 10 degrees south. So they want you to determine the airplane's displacement for the trip. And the first way of doing this is going to be with a scale diagram, and we're going to do with components of math and compare the results. So first of all, the question as it's written, is it a vector, addition, or subtraction? Well, we need to look at what we're given, right? In this question, the airplane flies a first leg of the journey, and then after that, it flies another leg of the journey. The total displacement would be the combination of those two, like what those two journeys they combine to be or add up to be, right? And so this is a vector addition question, right? The combined total, i.e. the two added together, gives the total resulting displacement. So this one absolutely is addition, the way it is worded, right? That's what it means, the physical reality of it. So yeah, and then this happens, and so they're added together, and just trying to emphasize how you choose, right? Because when you're looking at a question, it's pretty important to decide whether or not it's addition or subtraction. So let's look at in comparison to. Oh, and I could even, well, I'll do it when I do the diagrams, I guess. What about if the question was written this way? I've just clearly just modified this question to make it a very different question, but they seem kind of similar, right? So I'm showing you how easy it would be to modify this to make it mean something completely different. So this situation, the airplane starts with initial position of north 50 degrees west and 500 kilometers. So basically, they're starting at that initial position reference relative to Toronto. In other words, the plane is starting in Sault Ste. Marie. It's not traveling to Sault Ste. Marie, it's starting there, right? And then it ends up with a final position of 750 kilometers on a heading of east 10 degrees south. In other words, it ends up in Ottawa, right? And so determine the airplane's displacement. It can be the exact same question asked. In this question, we're given an initial position and a final position, right? And so the thing to recognize from this one is that displacement in our original vector lesson, delta D, the vector of it, is equal to the final position minus the initial position, which interchangeably often gets written as like D2 minus D1, right? So that's, notice that that's the logic of what we're doing here. And so all the way along here, we're seeing that this is a subtraction question this time. And it does mean a very different motion as well. Right? In one case, you're starting in Sault Ste. Marie and then flying to Ottawa. In the other one, we're starting in Toronto, flying to Sault Ste. Marie, and then after that, flying to Toronto. So total displacement, even though it's the same wording for the question in the end, means something a little different, right, in terms of the motion that actually happened. All right, so let's grab a screenshot. My plan was to have a little screenshot of this version and put that in here. We'll do the work, do with it. So shrink that down so it fits and we have all the information, easy access. And this version, traction. that one in here. We're going to do each of these in full. All right. That one down. All right. So here we go. We need a vector that represents 500 kilometers north, 50 degrees west, and we need a 750 and so on. So I'm just going to use a scale of 1 centimeter represents what? 1 centimeter represents 100 kilometers. Okay, so the scale we use is on the diagram itself, and then real life or whatever. Diagram 1 centimeter represents 100 kilometers. And so when you're looking at the 500 kilometers, so let's make that one a red vector. So I'll make it red writing. Obviously, that's just going to be 5 centimeters. Obviously, you could have talked about, this multiplication across is the second divided by the first, or in other words, we're dividing by 100. It's one of those easy ones where you probably wouldn't bother thinking about it. But it's nice to have that thought process available because it's not always as easy, right? And then let's make the other vector blue, I guess. And so it is 750. And so we're going to do the same division and get our 7.5. So I'm just going to be drawing vectors of 5 centimeters and 7.5 centimeters. Okay? And then the other thing we need is to visualize these things. So just as a rough visualization to start out with, we have north 50 degrees west. And so, a north 50 degrees west is going to look something like this. And so we're picturing this vector being 5 centimeters north 50 degrees west, right? That's the red one, actually. I'll change the color of that to match. And then the blue one is east 10 degrees south. And so these are just rough sketches just to give us an idea. East 10 degrees south and longer. So there's our 750 or our 7.5 centimeter line anyways, and our 10 degrees. Okay, and so the nice thing about that, just visualizing these things, at least we can picture what's going to happen, right? So when we have the addition of these vectors, even show that as well. Everything's grouped there. Yeah. All right. So let's just clone both of these guys. So we have this. So basically, we're going to travel this distance and then this distance, quite literally like that concept, right? And we're going to do this again, like I said, mathematically and also by scale diagrams. So let's do this scale diagram first. We need the 50-degree angle. And so I'm going to put on here, put up a grid, full-on grid. And then I'm going to show the direction. And we said the first vector was the red one, right? So let's make the red vector. This will change to be red in a second. But it's going to be in the 50-degree angle. Better put, just for functionality here, better put a line along there first. That way I can just measure. Oops, 10, 20, 30, 40, 50. The common error. If you were noticing that, you might have been trying to send messages to me telepathically and through time, I guess. Anyways, so yeah, so there's our angle and there's our north, south, east, west, and so on established. So this vector now, I can make be 5 centimeters long. Line this guy up decently here. It's not bad the way it is, but I'm fussy. All right, so there we go. There's the 5 and so on. So I can take this vector, I can put it starting there, and I can make it finishing there, and we can be pretty happy with that result once I tweak the beginning of it here. Oh, that to me, it's hard to know where they start and end here. Oh, you know what? I'm changing the black line, aren't I? That's why. All that good enough or what? Good thing you have the YouTube video, you can speed this up. Oh, look at that, I got it. All right. So shrink that one up just a touch. Anyway, so there, I think we're going to be pretty happy with that. I might just shrink it a tiny bit if I can get a hold of it again. Boy, kind of joy of trying to work with a smartboard program here is the layering and whatnot of things. Longer than I needed? I hope so. Oh no, I needed shorter. There we go. It's possible I'm trying too hard to do a good job, but I want the numbers from this process to match the result we get from the math, right? So there we go. So I'll label that as the 5, and I said this is going to be blue, or it is blue, I should say. It's going to end up being. So that guy there is not the right one. Apologize for this. It's a Friday. All right. I'm taping this anyways. It is. There we go. And so that is our 500. It represents 500. And it's at an angle of 50 degrees and so on. Getting an idea of how you would draw this. Probably wouldn't take you nearly as long. And then the 7.5 at an angle of 10. So now I need to go at this starting point here. I need to put that there. Again, put a little north, south, east, west grid. I'm just going to make one and then move it in there. Easier maybe if my mouse would keep responding here. Group in. And need to actually have my protractor the other way around because I want to make 10 degrees towards the south, right? I'll just flip this thing upside down and reposition it if needed here. Just like you'd do in real life, right? All right, so that's pretty darn good there. All right, so now line here, and I need to go 10 degrees. I'm just going to make this nice and long. Not into my math section over here, I guess, but there's the 10 degrees. Line up my ruler, get the 7.5 there. If I can, let's just call that close enough at the right angle. Starting there, and my blue representing my 7.5 or my 750. Right to there. Oh, that was less painful. All right. So that is our 10 degrees and our 750 and so on. There's 10 degrees. Yeah, this was kilometers here, of course, as well, and 50 degrees. And so what we're representing is the plane starting at this location. This is our start down here. Then it travels along the red path, and then it ends up finishing over here. So really, yeah, that's your path, right? Your displacement vector is just the vector that goes directly from start to finish, right? The whole idea of just end result comparison to the start. So displacement vector would be that thing that we're wanting to determine. Okay, so I'll write that in as the displacement vector, delta D. Matching color here, this is delta D, the resulting total displacement. So we have that set up, and then, yeah, at this point from the scale diagram, we're just measuring the angle and measuring the length, right? So we just go in and we angle. Oh man, it's close to 4, isn't it? I might just guess that it's supposed to be a nice answer of 4, which would, of course, convert with the ratios to be 400. And so we have the 4, and I can get the angle as well. So I'll just turn this guy around again and square in there. Good. So we've got 4 and an angle of 10, 20, 25, 26, 27. I'm going to say 27. Okay, so we got 27 degrees the spot there, and 4. So 27. I'll go purple again still. 27 degrees. I guess move my displacement label over a little. And then this measured to be 4 centimeters, which of course up here, if you had 4 centimeters, we would go the other way around. We'd multiply by 100 and end up with that representing 400 kilometers. Okay. So in other words, the plane started in Toronto, went to Sault Ste. Marie, where I was born, and then flew to Ottawa, right? And so the result is really the plane just ends up 400 kilometers away from Toronto in Ottawa. These numbers seem like they kind of make sense, right? Yeah, so or therefore here for this one would just be total displacement just equals the 400 kilometers, and we'd also say east 27 degrees north. And it points from Toronto to Ottawa quite nicely. So depending on how correct all the numbers are for the original trips and so on, we could maybe even compare to Google and just do distance from Toronto, Ottawa, and direction and see how it matches. But that would rely on these numbers being very, very accurate as well, of course. So let's not worry about the Google comparison, but let's do the math version now. Let me just use that over just a bit to make sure I have room. So the math version is going to have a lot of the same stuff. It just doesn't have to be as nice. So for the math version, I'll try and make it a bit nicer than these ones were. Like this is essentially what you want for this, right? You still want the diagram. Right? You just don't need to scale. So your diagram is going to help you analyze the numbers and keep track of things and so on, right? So we have our 50, right? So this is our 500, sorry. And it's at 50 degrees, right, as described in the question. And then you could show the longer one. I'll make it look similar to that one, right? The longer one that's at 10 degrees, something like this or whatever. So there's your 10 degrees. And then we get our result being this kind of line like this as well, just like the other one, right? So by accident here. I could use the purple line actually as well. We have like a representation of the same thing, right? So this is representing the displacement, and we're going to get our information from it mathematically though, okay? So it's not drawn to scale, but we can use it. So how this works is we need to calculate the x component of this. So let's call this like delta D1. I didn't mention that earlier. I'll say that now. Add this in. D2, right? When we're looking at the trips here, we have like one leg of the journey, delta D1, and this is delta D2. And then the total is like total displacement equals delta D1 plus delta D2, right? So that's the logic there. Just like this kind that we showed, that I showed earlier. Okay. So when we do this, we're going to get all these components and we're going to add them all up and we're going to get our total result mathematically. So we'll get this, reminding me to do that label so that I could say this is delta D1 x component. Then we have up here, the vertical one, we have delta D1 y component. Kind of heavy on labels, but it's good communication. And then here we have delta D2 x and y components. So delta D2 x component, delta D2 y component. We just have to calculate those things, right? So let's do that. We have delta D1 x component. So I would look at this automatically and say, okay, well, this is the 40 that is the complementary angle to make 90 degrees. So I work adjacent to the 40, and so it's just going to be the 500 kilometers times cosine of the 40, right? They're adjacent the 40. And so we're using cos. If you want to start from scratch, you can say cos of 40 equals, and then you do adjacent over hypotenuse, and you multiply to get this. But I am recommending, I'm encouraging you to take a bit of a shortcut there, because it's really what people do. Okay, so I don't interfere with my other side here, and then delta d. Oh, I should leave room for the answer. We'll just calculate the answer and then keep track of them. So delta dy is going to be the 500, and then we're opposite the 40, right? So it's going to be the 500 sine 40. So we can get values for that. Use the calculator all at once here. Delta d to x component, delta d to y component. Get some values here. So that'll work. So with the delta d2, see how we are adjacent to the 10. If I had have used the 50, it just would have been awkward in the path that I'm going to show you in the end. So, but if I had to use the 50 degrees, it would have been sine up here for the y, the x component, right? So I just want to make sure you know it's not always cos for x. It happens to be in this case the way I've done it. Delta d2 x component. So we're looking at adjacent to the 10, and so it's going to be the 750 times cos of 10, and the other one would be 750 sine of 10. Based on the same kind of logic, right? So let's do this. We've got our cos, looks like in degrees, and so 40, do cosine of it, and then multiply onto 500. 383.02. So that is this one. Could keep extra numbers if you want, but I'm not going to bother. Sine of 40. So 40 and sine of it times 500. Boom. 21.39. Sure I rounded right there. Yep. And 750 times cos 10. So 10 cosine times 750 equals 738.6. So 7, great color here. 738.61. If I'm rounding as I go, it would be better to keep floating decimal points, but it's just not worth the effort. Sine of 10. So 10 sine and times 750 equals. All right, so there we get 130.4. Okay, so there's all of our components for that. And then the magic at the end here is to think of this as like, okay, if I'm going to end up going from start to finish, so let's use a highlighter for this, but I am going to write in first. Let's do orange here. This is the start. This is the finish that we're interested in, right? And so the path along here, maybe highlighter might not be the best. I'll try it. Is you're going to go along here. It's too messy. I wonder if I can just change the size of it. There we go. So we're going to go along this way, right? And then we're going to go along this way because we know those numbers. And we're going to go along this way, and then we're going to go along this way. And all of those numbers are going to add up to be the grand total result, which obviously we could see on this graph because of the way it's arranged or organized here. Purple. It's going to be the result for this delta dx, right? The total displacement in the x and the total displacement in the y. Okay. A little messy there with my original displacement, so I'll just move it up there. And so then, just like I showed originally in the introduction to this stuff, it's 27 or something like that, keep track of your x's and your y's and get your totals and then calculate things. And hopefully we're going to get an answer of around 400 at around 27 degrees. Okay, so our x's and our y's. So we're going to have first on this journey, and this is where we need to sort of establish a reference frame as well. So we keep things the right signs relative to one another. So these are positive x's and positive y's. So my first x is negative, so that's a negative delta d1 x of 383. So negative 383.02. Then I'm going up delta d1y, so up 321.39. Then I'm going over now quite a ways, the delta d2x, so over a positive value in the horizontal of 738.61. And then the final is going down, that final y value, so down the 130. Okay. So that's what we have as our numbers. And so very much, you're just adding those up, right? You're just adding those up, getting your totals. So we're going to have the 738.61. So 738.61, and I'm subtracting the 383. Or you could do negative 383.62 plus the 738.61, but this is just how math works, so it's right. 354.99. And the other one, we need to do the 321.39. 321.39, take away 130.24 equals grand total there of 191.15. So, you know, this number, the delta dx, right, is that 354.99. And the delta dy is the 191.15. Okay, those are those numbers. What I recommend, though, is basically drawing that kind of a picture separately so that you can analyze carefully in the end. So just for simplicity here, I'm just going to draw that line, and I'm going to draw the total x and the total y, and I'm going to move those down, and I'm just going to change the color here to be green to match the idea of like I've added those up. Color coding on my lesson to help you interpret where things came from. And so we're going to have this stuff down here and this stuff. All right, so we're using that end result picture. If it helps, you know, you can even make this bigger looking and easier to keep track of and so on, right? And so we'll just transfer those numbers on and calculate the values. If it helps too, I might show something like, you know, what color do I want to use here? Like this picture is then, of course, you know, shown down here for clarity, you know, enlarge it, use it nice and big and proud and clear. And so here we go. We have this 354.99. We have this 191.15. And so we have a grand total then, mathematically, moment of truth coming up shortly here, delta D as a size will equal the square root of the sum of the squares stuff, right? So the 354.99 squared plus the 191.15 squared, and we have to take the root of that, and we'll see what we get. Hopefully around 400. 354.99. Need to square that thing. Then let's see if I can get away with this. I can just add that to the 191.15. Square that. Yeah, that's doing the right stuff. So that's my number there. And then I just need to square root it. So equals, let's just say, equals, yep. And then root it. We're getting 403. Look at that. That's pretty good, right? So 403. Thank goodness. Oops, I gotta get that number. So 403.18. So 403.18 dot, 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 you know, the kind of, well, actually, we can't really trust the rest of the decimals because I've actually rounded along the way, but obviously you can trust a certain number of decimals based on the number you started with, like we looked at in our significant digits lesson. Okay, so that is a pretty nice result. So that's the number of kilometers that scale diagram estimated. This is what it really is. And then the angle we can get from the diagram as well. So the angle, just pick a convenient angle in your diagram, and it happens to be an east, a certain number of degrees towards the north, right? Well, that's where you can just say, okay, well, theta equals tan inverse, because this is the opposite and the adjacent from that angle, right? So tan inverse of the opposite over the adjacent. Again, you could start with tan of theta equals this 191 over 354 if you wanted, but physics people do this. They just jump right to the calculation for the length and the calculation for the angle. So I can do 191.15 divided by 354.99, get that fraction, and then I can just do tan inverse of it. So boom, boom, tan inverse. It gives me 28.3 degrees, which we approximated as 27, so like we're off by 1.3 degrees. It's pretty good results. 28.3 degrees, right? And so in the end here, we have therefore, right? So therefore, the displacement, or I could have just done therefore delta D equals, but you get the idea, right? Is really 403.18 or so kilometers at east 28.3 degrees north. Okay, so that is the kind of work that you've been given extra time to do, right? Where you're going to, for a lot of the questions that were assigned, you've had a chance to do scale diagrams of it previously, and then now you're having time to do the component work and so on. So that's why I've given 2 days for this end result, because I want you might need to go back and redo some of those scale diagrams and fix mistakes or whatever. Okay, but time has been given there, so I hope you're using it well. I don't think I'll have time to do this whole thing because I have a class coming in shortly. But the main idea here is very similar, where you'd say, okay, I've got these vectors. So let's try. I'm just going to copy this whole thing, copy and paste in here. So the idea of this time is, I just have to ungroup this and get rid of some stuff. This isn't what we're doing anymore. We're not adding them up. Instead, we're saying that we have a start finish, right? And so, oops, I deleted the wrong one. We have this one we're not doing anymore because we're not adding them. Instead, we have a start and a finish. So what I need to do is I need to point out that we're starting here and we're finishing at this other one, right? So basically, we're going to put these, or that, so I can copy here. End up having to put these tail to tail. Okay, so, and it should make sense when I put this together here, where you say, okay, I started in Sault Ste. Marie right here. I ended up in Ottawa, and so then what's your displacement? Well, it's a very different beast, isn't it? Right? Your displacement is all the way from there to there, and the concept here is that we're subtracting those vectors, or the final position minus the initial position. So you'd do the same work. You would just measure it directly, right? And so you'd have that picture for the measuring stuff. And then it's a good thing I'm running out of time to do this, because it would be a bit of a nightmare to fit on this diagram. But concept-wise here is you'd still have all of your component work. The beauty, like if I had time to finish this, it wouldn't take as long as you think, because delta D x1 we already have calculated, right? Delta D x or y1 we've already calculated. Yeah, they're already all calculated, right? And so the reds and the blues or whatever can easily be shown on here. And then the idea of going from the start to the finish, I have my highlighter still. B. Hopefully it's still the little one. Yeah. So now we're going from start to finish. You're going to follow a path. You're going to go down this way, over this way, and then down this way, and then over this way. And that's going to give you an overall result of start, finish as an X, Y, as an X and Y component of your final. So this is your delta dx and your delta dy. And, from that, you're going to do the same stuff. You're going to do the Pythagorean theorem and get the angle and so on. Okay. So really, the only thing that's different is how we're lining up the vectors because of the different meaning of the story, a different physical situation. But this absolutely is really subtraction of the vectors, and then the one I did in full previously is addition of vectors. All right, so I hope that helps. As always, let me know if you have any questions. See you next time.